Okay, this is the key for the energy and phase changes worksheet. Before I get started, there are a couple things that I want to mention. The first thing is, if you're looking up here at the heat of vaporization, you need to know that the heat of vaporization is talking about when we are boiling or condensing. Okay, whereas the heat of fusion is if we are melting or freezing. This is important because in order to do these problems, you're going to have to determine which of these numbers that we're going to use on each one, and that'll let you know. The other thing here is in terms of talking about endothermic or exothermic, if it's going in the direction of solid to liquid to gas, that is an endothermic process. It requires energy to be put in to go from a solid to a liquid to a gas. Okay, so energy is taken in that case. If it's going in the direction of gas to a liquid to a solid, that is an exothermic process. Okay, which means it's releasing energy. Energy is being given off, which means in this case, delta H is negative. In this case, delta H is positive. So those fundamental principles will help you in each of these problems. I'm going to go ahead and start here on this first question. It's just kind of a concept question. It says, if you're looking at this chart above, compare the values for heat of vaporization and heat of fusion. So when we do that, you should see that the heat of vaporization numbers are quite a bit larger than the heat of fusion numbers. And then it says, like, why do you think this is the case? So here's what's happening. So first of all, you just have to identify heat of vaporization is larger than heat of fusion. And there are two things that are going into this. The first thing is that if you're boiling something, you have a larger separation of particles. Meaning if we're talking about a solid going to a liquid, they just spread out a little tiny bit. But if you're going from a liquid to a gas, they're spreading out quite a bit more. They're spreading out really, really far apart so that they're not close together anymore at all. And so the degree of separation we get for vaporization is much, much larger than the degree of separation we get for melting, for fusion. So the other thing that goes into this is vaporization has to fight against the outside atmosphere. So vaporization fights atmospheric pressure. And that requires more energy to be put in. Whereas in a lot of cases, melting and freezing is not too much impacted by the atmospheric pressure. Looking here, it says, what's the delta H when vaporizing 1 gram of ammonia? So we look back up here at NH3 at the top. We see that ammonia for heat of vaporization is 1,372 joules per gram. So that means for 1 gram. So in here we've got 1,372 joules. It says, is this process endothermic or exothermic? If we're talking about vaporizing, we're going from a liquid to a gas, and that process is endothermic. It says, what's the delta H when condensing 1 gram of ammonia? Well, this is the opposite process of evaporating. So it's negative 1,372 joules. All right. And then is this process endothermic or exothermic? This one is exothermic. So when a substance goes from a vapor into a liquid phase, the substance loses energy. So it has to give it off to the surroundings because of the law of conservation of energy. Any energy that's lost by the system has to be gained by the surroundings. So if it's losing energy going from a vapor phase down into a liquid phase, that energy has to be given off to the environment. So it's exothermic. Starting on these problems here, it says how much energy does it take for 4.6 grams of ethanol to boil? All right, so we look up at the chart above, and what we're looking for, since it says boiling here, is we're looking for heat of vaporization. So you look that up, you find it for ethanol, you see that it's 944.2 joules on that table above. And so then it sets up like this. 4.6 grams of ethanol, which is C2H5OH. That's the mass that we're given. We looked up above. We saw that it took 944.2 joules for 1 gram of ethanol to boil it. For sig figs here, the 4.6 has 2, 944.2 has 4, and then that 1 gram down there, that 1 gram is like a perfect 1 gram. The rounding in this heat of vaporization is given in the 944.2. So we don't have to worry about sig figs with the 1 gram on the bottom here. So that means that 4.6 is the lowest number of sig figs with 2, so our answer should have 2 sig figs. So it's 4,300 joules. We should keep in mind that this process here is going to be endothermic because it's boiling. It's going from a liquid to a gas. So it's going to be a positive value for our delta H. Continuing on here to problem number 4. It says, what's the delta H when 10 grams of water freezes? Is this process endothermic or exothermic? So if we're talking about freezing, we're talking about heat of fusion. So we start here with the 10 grams that were given of water. You look up the heat of fusion of water. You see that it's 334.0 joules for 1 gram of water. You multiply those together. We see that we have 3 sig figs in this one. You get 3,340 joules. However, it's important to note that this is a freezing process, which means that we're going from a liquid to a solid. Going in that direction, it's exothermic, so heat is going to be given off. So we need to throw a little negative sign here in front of our energy to indicate that it's exothermic, and that's our delta H. And then this one just says, is it endothermic or exothermic? It is exothermic. And again, just to explain how this makes sense here, that it's giving off energy, liquid water has more energy than solid water. So if we've got a liquid going to a solid, that energy that's lost in the water has to go somewhere, so it's released to the environment. That's why this is an exothermic process. Question number 5 here. This one's talking about benzene. It says, is the conversion of benzene from solid to liquid an exothermic or endothermic process? How much heat would be released or absorbed when 500.0 grams of benzene undergo this process? So we're looking at benzene. It says solid to a liquid. So solid to a liquid means that we are melting it. We're looking at heat of fusion then. The first question here says, is it exothermic or endothermic? Because we're melting, that's an endothermic process. Okay, the next thing we're going to do is set up this table here. We know that we have 500.0 grams of benzene. And then if you look up the heat of fusion for benzene, you see that it's 126.3 joules required to melt it for 1 gram of benzene. Multiply those together, we get 4 sig figs here, if you look in this one, so it's 63,150 joules. This is positive because it's endothermic. Okay, so that is our delta H. Number 6, it says argon gas is cooled to 86 Kelvin in order to store it at liquid state. This first thing is actually just a piece of information about what's going on in the problem, but it's completely irrelevant to the problem, so we don't care about the 87 Kelvin. That doesn't factor in. It says what's the delta H as 250 grams of argon condenses. So condensation here is the opposite of vaporization, so we're looking at H-vap. So on this case, you look up argon, find its heat of vaporization. We know that we've got 25.0 grams of argon. We know that it releases 162.7 joules of argon for every gram. Okay. So again, since this one is going from a gas to a liquid, it is exothermic, which means it's going to be negative. Rounding to 3 sig figs, we get 4,070 joules. Number 7 says a small pond contains 1.5 times 10 to the 4th kilograms of water, and in an especially cold winter, the entire pond freezes. Oh, poor fish. And then it says, as this happens, is energy absorbed from or released to the environment? How much energy is released or absorbed in the process? Make sure to watch your units. Okay, what that's talking about there at the end when it says to watch your units is that I've given you kilograms of water. We need to get it to grams of water. So 1.5 times 10 to the 4th is the same thing as 15,000 kilograms. Converting from kilograms to grams, we move the decimal place over 3 places to the right. So we end up getting, instead of 15,000 grams, we end up getting 15 million grams. If you're confused about that conversion, go and look at throwback number 1, which is on conversion of metric units, and I think that that should make more sense to you. So what we've got here then, we're going to start with this 15 million grams. Of water. Here we're talking about freezing water, so that's heat of fusion. So we use 334.0 joules for every 1 gram of water. This has 2 sig figs, so when you go through and multiply it all out, we get something like 5.0 times 10 to the 9th. Okay, this is an exothermic process because it's freezing, so that makes it negative for our delta H. Alright, and that is your answer there. And that means then that we get 5.0 times 10 to the 9th. Oops, this should say joules. Joules released because it's exothermic. Okay. So you might actually wonder in this last one where that negative sign went between the top answer and the bottom answer. The negative means released. It means exothermic. So the released is the same thing as saying that negative there. Okay, so we have this challenge problem here at the end. It says, what is delta H as 8.70 times 10 to the 25th molecules of CH4 are condensed? Is this process endothermic or exothermic? So in this case, we have to go through a stoichiometry problem on this one. I'll tell you this is not likely to be something on the test. It's just something to kind of push you to sort of review some things from the past. What we're going to do here is we're going to go from molecules of CH4 to moles of CH4. 2 grams of CH4, and then we're going to go to delta H. So this new conversion factor of, in this case, because we're condensing, we're using heat of vaporization, it allows us to do this. So molecules to moles, we're going to use 6.02 times 10 to the 23rd is our conversion factor, molecules to moles. Moles to grams, we have to use the molar mass. Okay, grams to delta H, because this is condensation, as I said, it's HVAP that we'll be using. So all of this looks pretty good. What we're going to do then is set up this conversion table. We get 8.70 times 10 to the 25th molecules CH4. Okay, then we know that for every 6.02 times 10 to the 23rd molecule CH4, that it's 1 mole of CH4. If you look up the molar mass of CH4 on the periodic table, you'll see that 1 mole of CH4 has a mass of 16.05 grams. Okay, and then we're going to use the heat of vaporization for CH4, so you look that up on that table on the front of the sheet. We get 480.6 joules for every 1 gram of CH4. So all the units here should cancel out. You go through, you plug it into your calculator. You should see that we have 3 sig figs on this problem because of the 6.02 times 10 to the 23rd and also 8.70 times 10 to the 25th. Those are both 3 sig figs. So you go, you calculate it out. You get 1,110,000 if you round it to 3 sig figs. This is an exothermic process. That's the next thing that it says, because we're talking about condensing. So that is exothermic. And if it's exothermic, that means we should have a negative sign on our delta H. Okay, so this should be negative for our delta H. All right, this is a kind of long number, so you might also write it as negative 1.11 times 10 to the 6th joules. That would also be acceptable. Okay, so that is that. Hopefully that makes sense to you. If you have any questions about that, make sure that you come and see me. This will be on the quiz at the end of the week, so make sure that you got it down.